When I think about the NOT gate, or inverter, I always picture it as a little switch that loves to do the opposite of whatever I tell it. If I give it a high signal, imagine flipping a switch on, the NOT gate goes nope and turns the output low. And if I send in a low signal, it flips that to high. It only has one input and one output, making it super straightforward. Mathematically, if I call the input x, the output becomes x prime, or x with a little bar on top. This just means the opposite of x. I use NOT gates all the time when I want to invert a signal in a digital circuit, like turning a logical yes into a no, or vice versa. This simple operation is surprisingly powerful when it comes to building more complex logic. The buffer gate, or BUF for short, is like a loyal assistant in my digital circuits. Its job is to take whatever input I give it and pass it along to the output, unchanged, no tricks. If I send in a high signal, it gives me a high output. If I give it a low, I get a low. But why bother using a buffer if it doesn't change anything? Well, sometimes I need to boost the strength of a signal, especially if I'm sending it to many devices, or maybe I want to add a slight delay. Buffers are also useful if I want to protect one part of my circuit from another, sort of like a bouncer at the door, making sure signals get through cleanly and safely. The symbol and the truth table make it clear. What goes in, comes out. Simple as that. The NAND gate is one of my favorites because it combines two basic operations, and NOT. Here's how I think about it. First, it checks if all its inputs are high, just like an AND gate would. But then it immediately flips the result. So if every input is high, the output goes low. If any input is low, the output is high. For two inputs, say x and y, the output is written as x and y with a bar on top, meaning the opposite of both being true. What's cool is that the NAND gate is known as a universal gate. That means I can actually build any other logic function using just NAND gates, making it a real workhorse in digital design. Now let's talk about the NOR gate. If I imagine the OR gate, it gives a high output if any input is high. But the NOR gate does the opposite. It only gives me a high output if all the inputs are low. As soon as any input goes high, the output drops to low. For two inputs, x and y, the output is written as x or y with a bar on top, so not OR. NOR gates are really handy when I want to create logic functions as simply as possible, often with just a single type of gate. The exclusive OR, XOR gate, acts a bit differently. I like to think of it as the either-or but not both gate. If I have two inputs, the XOR gate gives me a high output only when the inputs are different, one high and one low. If both are the same, whether high or low, the output is low. Mathematically, I show this as x with a circle plus sign y, which means exclusive OR. XOR gates pop up everywhere in circuits that need to compare things, like arithmetic operations or error checking. Their unique behavior is really valuable for making decisions based on differences between signals. The XNOR gate is like the sibling of the XOR. It's the equal or match gate. With two inputs, I get a high output only when both inputs are the same, both high or both low. If they're different, the output goes low. The mathematical symbol is just like XOR, but with a bar on top, meaning not XOR. I reach for XNOR gates whenever I need to check if two signals are equal, like in digital comparators or equality detectors. It's a simple way to spot matches, and the logic symbol shows that it's just an XOR with an extra inversion at the end.